Okay, so we're going to talk about relationships between electric and magnetic fields. These are some of the most interesting and surprising things that we see in physics. Unfortunately, or maybe fortunately from your perspective, the equations for them are too advanced to really be able to deal with in a high school level course. They rely on you understanding calculus. So we're just going to talk about the types of things we can observe in a more general sense without equations. But the equations that govern these relationships are together called Maxwell's equations. And a lot of them have their own names as well because Maxwell didn't discover all of these relationships, but it was him who put them together in kind of a unified way where he kind of saw the parallels between different relationships of electric and magnetic fields. And that's what we're going to talk about. Now, it turns out that electricity and magnetism are basically two sides of the same coin. So you can't necessarily have one without somehow having the other in one way or another. And that's why when we talk about the fundamental forces of nature, we don't talk about just the Coulomb's law, F equals K, Q1, Q2 over R squared. The fundamental force that we're talking about is really the force of electromagnetism or the electromagnetic force. And this is kind of a combination of the effects of electric and magnetic fields because they go together, they're two sides of the same coin. So we use B to indicate the magnetic field. And, oops, I spelled field wrong. And it is a vector in the same way that the electric field is a vector. And a compass points with the north along the field lines. So you might remember that when we looked at the magnetic fields in school, the magnetic field lines went away from the north and towards the south. That means that if you were to put a compass at this location, it would point towards the magnet. So this would be the north indicator of the compass. Just remember that the north indicator of the compass points along the magnetic field lines, which, yes, means that it sometimes points towards the south pole of the magnet. But the compass arrow follows these field line arrows. A lot of what we cover in physics lets us draw diagrams that have one or two dimensions involved, where we can always just kind of draw the angles flat on the page. But when we deal with electric and magnetic fields, we really have to work in all three dimensions. Which is another reason why we don't really deal with this stuff quantitatively, meaning with numbers, in this course. So we have up and down. We have left and right. But we also have this direction into the page and this direction out of the page. And you can actually probably see on my pen, it kind of makes a circle with a dot. So the symbol that we use for out of the page is a circle with a dot, meaning up or this direction. And the symbol that we use for into the page is a little X, And this comes from the idea of if the field lines were actual arrows that you could like shoot with a bow. Arrows have those feathers on the back of them. So if you look at an arrow from the back, it looks like this little X shape. So this means pointing into the page. This circle with a dot means pointing out of the page, kind of like this. Okay. So let's look at a couple of parallel corresponding relationships between electric and magnetic fields. First one we'll talk about, we have a magnetic field pointing into the page. So maybe there's a bunch of magnets nearby or something that's causing this magnetic field. And then we have a charge that is moving to the right. So we have this direction accounted for, and we have this direction accounted for. And it turns out that the force on the charge will actually be in this direction, perpendicular to both the velocity and the magnetic field. So essentially, as this charge is moving, it's kind of creating an electric field. So if you move through a magnetic field, you can measure an electric field that is perpendicular to both the magnetic field and the velocity. And an electric field means that this charge experiences a force. So, moving through a magnetic field, we get an electric field or a force on the charge. Those are almost the same thing. The electric field is force per charge. So we get a force that is perpendicular to both the magnetic field and the velocity. So if you take your hand and you make like an L shape and you can stick up one other finger, my thumb and my first two fingers are all perpendicular to each other, basically making almost like an XYZ set of axes. Okay. An important thing to realize is that it needs to be moving. So the force depends on the speed, the charge, and the strength of the magnetic field. Okay. There is a corresponding rule where we basically just switch the concepts of electric and magnetic fields. So, moving through an electric field we can measure a magnetic field that is perpendicular to both the electric field and the velocity. So here, these little circles are representing an electric field pointing in this direction, up towards the camera, out of the page. We've got a little spaceship flying really fast to the right. You need to be moving pretty fast to be able to measure this because it's not a very strong effect. So we have our velocity pointing to the right. We have an electric field pointing out of the page, and that's going to create a magnetic field pointing up. So, same set of concepts. It's technically the opposite direction. Here, our B was pointing into the page. Here, the electric field's pointing out. But, moving through a magnetic field, a charge will experience a force that is perpendicular to both its movement and the field. Moving through an electric field, we get a magnetic field that is perpendicular to both the electric field and the movement. And that's why we need all three directions, which is why we need to introduce these symbols. Cool. The stronger the field, the faster you go, the stronger the effect for both of these things. All right, now we're going to go through one more set of relationships. It's closely related. It's pretty similar, but these ones will be a little more fun because I actually am able to physically demonstrate them for you. So we have Faraday's law. Faraday's law basically says that if the magnetic field going through a loop changes, there will be an electric field that pushes charges around the loop. So, let me try to show you what this actually looks like. I've got a toilet paper tube and I've wrapped an aux cable around it a bunch of times so that we can hopefully measure the field that will be pushing the charges around this loop. I've attached the two ends of the cable to the probes on our multimeter, and if the charges are being pushed around the loop, that means that we will measure a voltage. It's a little bit hard to keep the two sensor leads connected, so I'll just double check and make sure that it's ringing here. Okay. We're going to put it on the most sensitive voltage setting. And then I've got these pretty strong magnets that I'm going to hold on to with this paper clip. And when I bring the magnets close to the loop, that means that the magnetic field through the loop is changing, and that's going to cause an electric field that pushes the charges around the loop. Notice that when I'm holding the magnet there and holding it still, it's not reading anything. That's because even though there is a magnetic field in the loop, it's not changing. But if I pull it back out, then while I'm pulling it out, we also see a voltage, meaning charges are being pushed around this loop. I'll show you again. Put it in, I get a reading. Pull it out, I get a reading. Cool. So hopefully that convinces you that this really is true. If we change the magnetic field going through a loop, we can get an electric field that pushes the charges around the loop. That's called Faraday's law. Okay? So hopefully you can kind of feel what's coming next. We're going to do the same rule, except that instead of, we're basically switching the roles of the magnetic and electric field. So if the electric field going through a loop changes, there will be there will be a magnetic field going around the loop. Okay, so just like with these two relationships, these two statements are essentially the same, except that I just switched which one is which, electric or magnetic. But we don't have magnetic charges exactly. We have the north and south poles, but we know that we can't like separate those into separate pieces. We do have electric charges, which means that we can have electric current. And it turns out that changing the electric field is similar in its physics results to just having a current. So, or there is a current. That's why I left a little bit of space here. So we're kind of adding one extra thing to this, which is we can get a electric field going around based on a changing magnetic field going through. We can get a magnetic field going around based on either a changing electric field or a current. The current does not need to be changing, but the electric field does. Just like we saw when we held the magnet inside the cable, it didn't do anything. It was only while it was moving, while it was changing. So we need to have something moving essentially for these additional fields to get created. Either charges moving, creating a changing electric field, or creating a current. Let's see an example of this happening. So here we have from the circuit kit a little electromagnet. And what this is basically it's got a coil of wire, like a better version of the toilet paper tube on the inside. And when I cause current to flow through this thing, that's going to create a magnetic field. This drains the battery, so I don't want to do it for too long. But I've got a little nail here to show us the effect of that magnetic field. And when I connect this up to the two sides of the battery, let's see what happens. We get, I can feel it. There we go. We get a magnetic field. And this is not because this is a permanent magnet. It's not like the fridge magnet that I was using before. If I unplug the battery, the magnetic field goes away, because that was basically a temporary magnetic field caused by the current flowing through this. So we can get a magnetic field from a current, and we can get a current from a magnetic field. So this is just kind of the tip of the iceberg in terms of electromagnetism, but it's a super cool topic, so I hope you're excited to learn more about it when you take Physics 2 in college. Hope everybody's having a great week. Let me know if you need anything. Talk to you soon.